Welcome back to one more video on application of flexibility matrix method for analysis of continuous beam. Since flexibility matrix method is a force method, there are various ways to choose unknown redundant reaction in beam. So after watching this video, you will be able to analyze continuous beam using two different ways. So for that, we will consider this beam. This is a continuous beam with three supports. Support A is fixed support and B, C are roller support. So there are total 5 reactions in the beam, 3 at A and 1 each at B and C. So here degree of static indeterminacy is 5, that is total number of reactions, minus equation. So equilibrium equations are 3. So 5 minus 3 is 2. So degree of static indeterminacy is 2 in this case. And therefore we have to consider any two reactions as redundant reaction to solve this beam using flexibility matrix method. So in first video, I will explain you how to analyze this beam by considering MA and MB, that is moment at A and moment at B, as redundant forces. In this video, I will explain the application of conjugate beam method to develop flexibility matrix. In second video, we will consider RB and RC as redundant forces. So in this video, I will explain application of unit load method to develop flexibility matrix. So this is the difference in first way and second way. In first way, we will consider MA and MB as redundant forces and we will apply conjugate beam method to develop flexibility matrix. Whereas in second way, we will consider RB and RC as redundant forces and we will apply unit load method to develop flexibility matrix. So let us start. So this video is about analysis of continuous beam using flexibility matrix method, considering MA and MB as redundant forces. So step number 1 in flexibility matrix method is always to calculate degree of static indeterminacy. As you know that we calculate degree of static indeterminacy, which is equal to number of support reactions minus number of equilibrium equations. So in this case, degree of static indeterminacy is 2. Step number 2 is to identify redundant reactions. So in this case, we are going to consider moment at A and B, that is MA and MB, as redundant forces. Now the basic equation in flexibility matrix method. You know that the equation is dr is equal to drl plus f into r. Now let us understand the meaning of each of these terms. Now dr means displacement in the direction of redundant reactions. So in the direction of redundant reactions, we consider the coordinate and we write what are the displacements in the direction of that coordinates. So that is dr matrix. Next is DRL matrix. So here the size of the matrix, DR matrix, is ds by 1. If degree of static indeterminacy is 2, then size of DR matrix is ds into 1, ds by 1. Second is DRL matrix. So DRL matrix means displacements in released structure due to load in the direction of coordinates. So here, since MA and MB are the unknown redundant reactions, so we will consider coordinates at 1 and 2, that is at A and B. So DRL matrix will have size ds by 1. That means in this case, the size of DRL matrix will be 2 by 1. Next is flexibility matrix. So flexibility matrix has size ds by ds. That is, if degree of static indeterminacy is 2, the size of flexibility matrix is 2 by 2. The last one is R matrix, which is redundant forces. Now here we are considering MA and MB as redundant forces. So here the size of this matrix is ds by 1, which is 2 by 1. Now next step is we will generate all these matrices. So first of all, we will generate matrix of redundant forces. So for that, you have to consider the coordinate system in the direction of these unknown reactions. Unknown reactions are MA and MB. So we will consider coordinates in the direction of MA and MB. So here redundant reactions are MA and MB. So this is R matrix and this is the unknown matrix which we want to calculate. We want to calculate the values of MA and MB. Then next matrix is DR matrix. So in DR matrix, DR matrix means displacement in the direction of redundants. Redundants in this direction, if there is some slope which is already there in the structure, if there is some displacement in the direction of this movement due to any reason, then that will appear here. Here, if there is a given slope at 1 or 2, then that will appear here. But there is no unknown slope, there is no known slope available here. So DR matrix will be 0, 0. Normally it is 0, 0 matrix. Next is DRL matrix and F matrix. To generate this DRL and F matrix, we are going to use conjugate beam method. Let us understand how to develop DRL matrix. DRL means displacement in release structure due to load. Now for that, we will be using conjugate beam method. So I suppose you know this method, conjugate beam method, to calculate slopes and deflection. So to calculate slopes and deflection by conjugate beam method, what are different steps? So here, first of all, we draw the release structure. Then we draw bending moment diagram due to load, draw conjugate beam for that, and then calculate displacement in the direction of redundant. So you know that conjugate beam is an imaginary beam which is loaded with M by EI diagram of original beam. So to draw the conjugate beam, first of all, we have to draw the bending moment diagram due to load. The bending moment diagram itself is considered as load on the conjugate beam. And for conjugate beam, if you calculate the shear force, it will be equal to slope in the original structure. And if you calculate bending moment in conjugate beam, it is equal to deflection in original structure. So I assume that you know the basics of conjugate beam method to calculate slopes and deflection. So this is the given beam and we are now developing DRL matrix. DRL means displacement in released structure due to load. Now first of all, we have to draw the release structure. So what is the meaning of release structure? In this continuous beam, we are considering MA and MB as redundant. So first of all, we have to remove the capacity of this A and B to carry MA and MB. That means remove MA and MB from this original beam. So how we can remove MA and MB from this beam? By making hinge here. So release structure for this will look like this. So if you introduce hinge here, it will become, it cannot take any moment. That means MA and MB is equal to 0. And therefore, this is called as release structure when MA and MB are redundant. So when we consider here hinge, we can separate the beam in two parts like this. So one is with UDL and second with point load. Now for this beam, these are the given beam. For this beam, we have to draw the conjugate beam. Why we are drawing the conjugate beam? Because we want to calculate what is the slope here due to this given system of load. So what is the slope here in release structure? Displacement in release structure due to load. What is displacement? Displacement is slope. So we want to calculate slope at A and slope at B. You know that slope at A and slope at B in given beam is equal to shear force at A and shear force at B of conjugate beam. Therefore, we are interested in calculating shear force at A and shear force at B. Now, shear force at A is nothing but the reaction of conjugate beam at A, and shear force at B is nothing but reaction at B of conjugate beam. That is change in shear force, not shear force, it is change in shear force at B. So it is equal to this reaction at B in conjugate beam. Now how to draw the conjugate beam for this? As I told you that conjugate beam is an imaginary beam, which is on this beam the load is bending moment diagram. So for that, first of all, we have to draw the bending moment diagram. So here, if you calculate WL square by 8, you will get 120 kilonewton meter. And if you calculate WL by 4, you will get 75 kilonewton meter. So these are the bending moment diagram for portion AB and BC. Now to this, we consider this as now load on the beam. And since these are the simple supports, the supports remains as simple in conjugate beam also. So this beam is now converted to conjugate beam. And what we want to calculate? We want to calculate displacement in release structure due to load. That means theta here, displacement corresponding to the coordinate. Displacement corresponding to coordinate at A is slope at A, and coordinate at B is slope at B. So here displacement in original structure, that is slope in original structure, is nothing but shear force in conjugate beam. So if you calculate this RA dash, it will be equal to DRL1. And if you calculate this RB, which is addition of RB1 and RB2, that will be DRL2. So we are using conjugate beam to calculate DRL1 and DRL2. So now we are considering this bending moment diagram as load on conjugate beam. And since we are interested in calculating slopes at A and B, we have to calculate these reactions. So let us first calculate RA dash, RB1 dash and RB2 dash. So RA dash and RB1 dash, since the load is symmetric, it is half of the total load. So we can calculate like this: RA dash is equal to RB1 dash, which is half of this parabolic load, which is 2/3 base into height. So we get 160 upon EI, which is reaction at A of conjugate beam. Similarly, from this triangle, this is also symmetrically loaded. So we can directly calculate half of the total load, which is 56.25 upon EI. Now DRL1 is nothing but slope at A, which is equal to RA dash, and DRL2 is nothing but the slope at B, change in slope at B, which is nothing but addition of RB1 and RB2. So let us calculate. So DRL1 is shear force at A of conjugate beam, which is equal to 160 upon EI. Just now we have calculated. Similarly, DRL2 is equal to RB1 dash plus RB2 dash. It is equal to 216.25 upon EI. So this is how we develop DRL matrix using conjugate beam method. So you can take this 1 upon EI outside the bracket also. So it will be 160 and 56.25. So this is how we can develop DRL matrix. Now we will develop flexibility matrix. The size of flexibility matrix is 2 by 2 because here unknown redundant reactions are 2. So we first develop or generate first column of flexibility matrix. So you know that flexibility coefficient means the displacement. If you designate one F11, it means displacement at 1 due to unit rotation at 1. F12 means displacement at 1 due to unit rotation at 2. So this is the basic definition of flexibility coefficient. So here we are first developing first column of flexibility matrix. That means F11 and F21. That is first column of flexibility matrix. So to generate first column of flexibility matrix, we have to give unit rotation in the direction of first coordinate. So we will apply unit rotation like this, and then to calculate the displacement due to this unit rotation, we are using the conjugate beam method. So for that, to calculate the displacement, first of all, we have to draw the bending moment diagram for this. So since there is no load on BC portion, there will not be any bending moment diagram. So here for AB portion, here the bending moment is 1. So bending moment diagram is like this. And conjugate beam, you know that it is the imaginary beam which is loaded with bending moment diagram of this original beam. So the conjugate beam will look like this. Now what we are calculating? We are calculating F11. And F11 means displacement at 1. Displacement at 1 due to unit rotation at 1. So what is slope at 1 due to unit rotation at 1? It is nothing but shear force at this level. So shear force of conjugate beam at this level is nothing but reaction at A. So F11, if you solve this beam and if you calculate reactions, then this RA dash is nothing but F11. Now F21 means displacement at 2 due to unit rotation at 1. So what is displacement at 2? That is slope at 2. So slope at 2 corresponds to shear force at 2 in conjugate beam. Therefore, R dash B is nothing but F21. So let us solve this and calculate the flexibility coefficient in first column of flexibility matrix. So to calculate the reactions, first we will take summation of moment about B equal to 0. Consider portion AB only. So what is the equation we will get? RA, here there is RA. So RA dash into 4 is equal to area of this diagram. We are taking moment about B. So distance is 2/3 of 4. So if you calculate this, you will get 4 upon 3 EI. So what is RA dash? RA dash is nothing but the flexibility coefficient F11, which is nothing but the slope at 1. And slope at 1 is equal to shear force at 1. So it is equal to RA dash. So F11 means displacement at 1 due to unit rotation at 1, and it is equal to RA dash. Now second element of first column is F21. So for that we will take summation of vertical forces equal to 0 because we want to calculate R dash B. Why we are calculating R dash B? Because we want to calculate slope at B. And slope at B is nothing but it is equal to shear force at B of conjugate beam. So we know RA dash. So we can calculate RB dash by taking summation of vertical forces equal to 0. So if you apply this, so total load is equal to RA dash plus RB dash. So we get RB dash is equal to 2 by 3 EI. And this RB dash is nothing but F21, that is displacement at 2 due to unit rotation at 1. Displacement at 2 due to unit rotation at 1, which is equal to 2 upon 3 EI. So this is how we can generate first column of flexibility matrix. Now we will generate similarly second column of flexibility matrix. So for that we will apply unit rotation in the direction of 2. It will look like this. So for this case we will draw the conjugate beam. So for this case we will draw the bending moment diagram, which is nothing but the load on conjugate beam. Now what we want to calculate second column means F12 and F22. What is F12 means? Displacement at 1 due to unit rotation at 2, which is nothing but RA dash. So F12 means displacement at 1 due to unit rotation at 2. And displacement means theta. And theta corresponds to shear force in conjugate beam, and therefore F12 is RA dash. So similarly we can calculate taking moment about B equal to 0 for span AB, we can calculate RA dash as 2/3 of EI. And therefore F12 is equal to 2/3 of EI. Then what is F22? It is displacement at 2 due to unit rotation at 2. So what is slope at 2? It is nothing but shear force at 2, which is addition of RB1 dash plus RB2 dash. So we can calculate RB1 dash like this. So by taking moment about A equal to 0, you can calculate RB1 dash. What will be equation? RB1 dash into 4 is equal to moment of this multiplied by 2/3 of 4. So 4 will get cancelled. Therefore, I have not written here 4. So you will get RB1 dash as 4 upon 3 EI. So what is RB1 dash? It is contribution in this slope from this part. So we have to calculate RB2 dash also. So similarly, we can calculate RB2 dash, we will get 1 upon EI. So what is F22? F22 is displacement at 2 due to unit rotation at 2. So displacement means slope, and slope is equal to the shear force in the conjugate beam. And therefore F22 is equal to RB1 dash plus RB2 dash. So if you add these two, you will get 7/3 EI. So this is how we can develop the second column of flexibility matrix. So if you write this in matrix form, it will look like this. Now after developing flexibility matrix, what you have to remember? You have to remember that the elements of flexibility matrix on the diagonal, you must get all positive values. Of the diagonal, there can be negative value, but on the diagonal, there must be positive values. And these values are same. That is, this is a symmetric matrix. Therefore, this is F12 and this is F21. So F12 is equal to F21. So this is how we have developed all the matrices in the basic equation. So the next step is to solve this flexibility equation, which is dr is equal to drl plus f into r. So substitute the values. We will get like this. 0 is equal to, this is drl matrix plus f into r. R means redundant moments. Now here 1 upon EI you can take outside the bracket, and since left side is 0, 0, you can neglect 1 upon EI. So these matrices you can solve using, you can write the simultaneous equation for this, or you can use Gauss elimination method to calculate MA and MB. So if you write the simultaneous equation, it will look like this. 0 is equal to 160 plus 4 by 3 MA plus 2 by 3 MB. This will be first equation, and second equation will be 0 is equal to 216.5 plus 2 by 3 MA plus 7 by 3 MB. So if you solve these two equations, you will get MA is equal to minus 85.875 and MB is equal to minus 68.25. So this is how we can calculate the redundant moments in the structure. And you know that in this structure, moment at C is equal to 0. So once you get this, you can draw the bending moment diagram. So after analysis, we got this result. Bending moment at A as minus 85.9, bending moment at B at minus 68.28, and bending moment at C is 0. So let us draw bending moment diagram. So for that, draw a baseline. At A, draw ordinate minus 85.9. At B, draw ordinate 68.25. Join this. Then at C, bending moment is 0. So join this like this. Over this, we superimpose the bending moment diagram due to load. So due to 60 kilonewton, it is WL square by 8. And due to 100 kilonewton, it is WL by 4. So if you superimpose, it will look like this. So this is the bending moment diagram for this beam. Now, how to draw the shear force diagram? So in my other video, in which we have considered RB and RC as redundant, in that video, I have already explained how to draw the shear force diagram for this case. And that shear force diagram looks like this. So do watch that video to understand how to draw the shear force diagram and how to calculate these various quantities in shear force diagram. And in that video, I have already explained how to calculate the point of contraflexure also. So to understand how to draw the shear force diagram and how to locate the point of contraflexure, do watch the video in which we have considered RB and RC as redundant forces. So that is the second way to analyze this beam, the same beam, using flexibility matrix method. I will provide the link of this video in description box. I hope you will find this video useful. Thanks for watching.